topology optimization. Let's talk about topology optimization. We have a partner called CAESS, and they are providing a nice solution called ProTOpCI, and this solution is available in Creo 3, and with this solution we can do easily topology optimization within Creo parametric. We see here an animation of a part which will be optimized. It's loaded here, it's supported here, and ProTOpCI is taking out the material where it's not needed. Even in the time of 3D printing, we have to make sure that we have the right lattices in the right position. ProTOpCI is also taking care about these lattices, as we can see here in this nice animation. Or another example down there, we have a pedal, and we'd like to take out the material where it's not needed, and ProTOpCI is doing the job for us. How does this ProTOpCI working? We are starting in a Creo parametric environment. In Creo Simulate FEM mode, we are taking the room, the placeholder which can be optimized. We are assigning materials, we are defining load cases and constraints, and then we are meshing our part with, let's say, H elements. Then we are transferring that component to ProTOpCI. There we are adding some, let's say, technical constraints like symmetries and other things, and then we are starting the optimization in ProTOpCI. ProTOpCI is taking out the material where it's not needed. We can see it right now in this animation. So it's analyzing the part, it's analyzing the stresses, and where the part has no stresses, it takes out the material. And so ProTOpCI is providing for me an optimized geometry which can be transferred afterwards to Creo parametric as STL file, and with the help of an STL file we can model a new component, and with that component we can do the fine-tuning, let's say, from structural side with Creo Simulate, and we can analyze the Creo part in Creo Simulate native mode. Let's have a look at that in real time. So we're changing right now to Creo parametric 3.0, and we're going to a little assembly I created in Creo parametric. We see right now in this assembly the optimized STL file is already in it. We don't need that component, so I'm going to delete that one. And here I created this environment, and with that environment I'm going to define my simulation model. I will be here in the FEM mode of Creo Simulate. So what did I here? I mean, in that environment I said, okay, I'm constraining these surfaces here in that pin, and between that pin and my bracket material here in blue, I created a small layer, and I will use that layer later on in ProTOpCI for a contact feature. I also assigned here some materials to some regions before I created a region in Creo Parametric or in Creo Simulate. We call it the simulation feature volume region. So I separated in my bracket part these red marked volumes, and these red marked volumes, they should stay later on as, let's say, cat regions in my optimized part. So I'm creating some sub volumes, and then I'm assigning materials to that sub volumes. Here I created 4 materials, one aluminium cat, one aluminium optimized, and stainless steel, and stainless steel for contact layer with these material properties. Of course, here I'm going to assign these materials to my component. As you can see it here, the normal aluminium or the aluminium cat model is this volume regions, which I want to keep for my optimized part. Here I have my normal aluminium region, which can be optimized, and I created the steel material for the pin, and I assigned steel material for the contact layer. Then I already explained here the constraint set. So I constrained these 2 pins here, and in the other regions in that pin here I created 3 load cases. One load case is here in that direction, 2000 newtons. One load case is in 30 degrees direction here, 2000 newton, and the other load case is in that direction here. So here are the load cases, and as we can see here, that are the loadings for that situations here. Okay, and then I'm nearly done. Of course, I will create some mesh refinements. When I'm doing a mesh, a standard mesh with the standard settings, the mesh will be 2 cores, as we can see it here, for an optimization task. So I went here and I brought in mesh controls. One mesh control is here for all the parts. I said, okay, I want to have maximum mesh size of 6 millimeters to bracket and the pins. In the real life, I would take here maybe a mesh size of 2 or 3 millimeters, but for the reason of the time, I will take right now 6 millimeters. And the contact layer here, I did here a mesh control of 2 millimeter because the thickness of this contact layer is 2.5 millimeters, and we should have here, let's say, 2 layers in that contact regions. Okay, and that's all what I'm going to do for this model setup. In addition to that, here I set up a new or 3 new analyses here. I can redefine that one, and as you can see it here, I have a static one with my constraint and appropriate load set. So right now I have 3 let's say analyses here, and then I can transfer these models here to ProTOpCI. So right now I have this mesh size. I'm going to mesh it again here. This is for ProTOpCI. It's still a little bit too coarse, but as I explained before, that's because of time. I'm doing quite a coarse meshing, and now I'm transferring that model to ProTOpCI. So that means an FNF file, that's a finite element file, will be created and will be loaded in the nice ProTOpCI application of CAESS. And this application is starting right now. I can see right now here my 3 load cases. I can configure my model to be able to see the model here in 3D. I can say I want to see also the mesh here, and then I can move my component in the main window. I will prepare my model with, let's say, materials or material regions. So all the 4 materials I created will be transferred to ProTOpCI, and of course these material regions, they are assigned to, let's say, a volume or a part, and I say, okay, this material aluminium CAD is just a fixed region, so ProTOpCI is not allowed to optimize this region. Also, the pin, which is made of steel, is fixed geometry. Only here the aluminium material, which is assigned to the bracket component, this material is free to optimize, and my contact layer here will be used for a fixed contact volume. I can show this information, and right now color coded I can see here, okay, blue is the optimized region, or the region we can be optimized. Here green we see our constraint, and purple we see the load regions, and in black we can see the contact layer, and gray is the fixed geometry. Then we can go in and say, okay, we wanna bring in, let's say, also some technology constraints. That means I can add here some constraints, and one constraint might be I want to have my optimized material here as a plane symmetry, to that plane I can see right now here in the main window. I'm going to add an additional option here. It's called bidirectional open constraint, and this will be used for a casting, like a casting form, and as I show it here also, the casting is defined then in a way that the casting form can be opened in those 2 directions. That are capabilities to tell the optimizer in which direction he can take out the material. So that's all I have to define. And now I can go for my optimization task, and I can start the session. Before I'm starting the session here, I'm defining a target, and I say, okay, I want to have here a target of, let's say, 25%. So I want to bring down the volume to 25%. So right now the solution is starting with that actual geometry, and it's taking out, or it's analyzing my model. I can see here during this optimization the displacements on my part. Now I see the displacements. I can see here also the influence of my 3 load cases, and as I can see here, the load case number 3 is that one which influences my part, because this load case 3 is acting in that direction, and that causes here a big moment, and these 2 load cases are not that important. So right now it's taking out the material where not needed, and because of, let's say, time reasons, I'm going to pause my optimization, and for this demonstration I only want to use here the load case 3, that my, let's say, optimization is running quicker. So I'm ending that session. I'm going back for my model, and I'm just activating the load case number 3 with that big impact factor. I'm going back for the optimization task. My target will still be the same, and I'm going to start the session here. And now the optimization starts again from beginning, of course, right now only with that load case, and of course right now or still with a coarse mesh. So we won't see, let's say, the super trooper optimization. We will see the behavior of the optimization task. And right now it runs very quick because of one load case, and ProTOpCI is taking out the material where not needed. Right now I'm looking at the displacement. I can go in here for, let's say, the stresses. I can change here also the scale to see where are the stresses, to get a better feeling about the behavior of this topology optimization. During this task I'm also able to smooth a little bit the surfaces, to see some cross-section, to have an idea how it looks inside. I have also possibilities here to see perspective projection, to have a better feeling. And right now we see the optimization task within ProTOpCI, and we see right now we already have 14 cycles, and the actual volume ratio came down to 32%, so we are quite close to 25%. And as soon as ProTOpCI is optimizing my part in, let's say, around 25%, the optimization task will be stopped. And we see right now we are quite close to 25%, and soon we will see the optimized part. If I'm in a hurry, I can say, okay, I wanna stop here, I wanna pause my optimization and transfer the actual model to Creo parametric. I'm waiting another 20 seconds until ProTOpCI is stopping my optimization task. Okay, we have 25.8%, and now the session has been stopped. And I can have a look at my optimization component. Of course, when I'm looking here at that region here, I only have 2 layers of elements in that region, and I wouldn't take that result in reality, but for demonstration reasons that's okay for me. And now I have the capability here in ProTOpCI to have a look at my geometry, to smooth and export the geometry. So I'm going here for smoothing and exporting. I'm going to check my geometry. I can remove here, let's say, the peaks. Depending on the bandwidth, I can remove them. I can also go in and, let's say, depending on a bandwidth, I can smooth the cut edges here, okay, to get, let's say, a nicely rounded geometry. I can check this geometry. I can do some further simplification, things like that. But at the end of the day, I want to export this geometry back to my, let's say, simulation environment. And in my simulation environment here, I'm working here in that directory. Okay, ProTOpCI, I want to save here my data as an STL file, and I say, okay, that's a file called live. Okay, this file has been saved, and now I can go back for Creo parametric. And in Creo parametric, I can, let's say, open that component I'm setting my filter to all component. I can see that STL file, and now this STL file will be shown here on my screen, and with the help of that STL file, I agree it's too coarse, I can reconstruct a new component, as we can see here in that environment. So in that environment, I took a nicely optimized component with 3 load sets, and then I constructed with that help here. I constructed here that component, so I was just taking here the same position of that components, and then I went in and I created here with some, let's say, sketches here. I created a similar component which might be easily, or which can be easily casted. I made some roundings, I made some fillets, I made some chamfers, things like that, to get that part. And at the end of the day, I can take that part and I can go with that part to the Creo simulate native environment. Of course, on that component I can set up my analysis, and in that result file I just can go in and I can analyze my component with that load sets, and I can see then my displacements. And of course, in that environment I will also have the capability to have a look at stresses, and in that case I want to see, let's say, a deformed shape. Of course, I can see here also my undeformed behavior. That are the capabilities Creo Simulate is providing for me in or with the help of ProTOpCI from CAESS. Thank you for your attention.